All right, in this video, we're going to be implementing boosting in R. So let's get this set up. Boosting, as we're going to use it, lives in a library called GBM for gradient boost method. Again, try to run this thing. If it loads, that's great. If not, packages, install GBM, and you should be all set. So GBM builds the boost model exactly as we described. The individual boost models are small trees, very, very small trees, so just a couple of splits, which is nice for comparison purposes because our bagging method is also trees. So we're comparing bagged trees to boosted trees, and that's conceptually really, really nice. So let's do this thing. So let's say boost equals, and then it's GBM is high val as a function of all available variables, data coming from training, and we need to say two things here: the number of trees, and we'll do 5,000. But then, as we mentioned, the problem with this thing is that it can be really overfit. So we're going to do cross-fold validation, and we need to tell it how many folds we want. So remember, folds is like how many pieces are we going to break the training data set into, and then kind of rotate through those folds as our little validation or mini test. Here, let's do 4-fold, just to do something, just to prove that we can. The data set, the training data set is not that big, so we don't want to break it into many more than 4 pieces because they'll get too small. But let's see how this goes. So we'll run our boost here. It takes a little second because it's doing quite a bit of computation. And then the question is, how do we actually see the thing? Well, let's do down here gbm.perf. So that's performance. That's GBM performance. And then I'm going to move my face up here. So this is the most important figure for the entire course in R. So this black curve here is the error on test, essentially. Green is the error on the cross-validation partition, which is an estimate of our error on test. And notice that it goes down and comes back up. So our 5,000 was way too many. Like, we didn't need that many. In fact, the best number is this dotted blue line here. So it's like a pretty small number. In fact, 103. So this 103 is the best number here. And the thing is, like, I put in 5,000 because you kind of you have to make it a little bit too big in order to make sure that you're getting this lowest point. So you don't really know at first. So try a biggish number and then see what this figure looks like. But it's pretty awesome. I mean, I think this is the first time we've seen this figure out in the wild in a data ecosystem. But this is the thing we've been talking so much about. This is the thing that's trying to help us control for overfitting. The awesome part is if we say best size equals gbm.perf, it gives us that number. So boost like this. When I say best size here, notice I have a new variable that's 103. That says that the boost depth should be 103 trees. Not all the way up to the 5,000 that I made. Stop at 103, which is awesome. It's just so cool to see something you've thought so much about conceptually actually pop up in practice. So how do we actually do this thing then? So let's do pred boost equals predict boost test, just like you would always think. But you now need to say, well, what part of the boost do I want to use to make my predictions? Do I want to use all 5,000 trees in the boost? No, I want to use best size. So you say, actually, I know you have 5,000 trees in this boost, but when you get to the 103rd, stop there because everything else is just going to make matters worse. It's going to start to overfit. And let's run this and see how it goes. So pred boost, and look at 1 through 10, just to see what's going on. Again, like when you see things like this, it's like, okay, there's something going on. These are not probabilities. These are not these are not zeros and ones. These are not trues and falses. Something is going on. And so if you went into the documentation, this is an internal representation of the strength of the prediction right now. And instead we want to say, instead of that, we want type equals response. So this is the same, for instance, as like logistic regression. When we did this, we want to give the type equals response. And if I do that and look through here, now these are the probabilities. Okay, thank God. All right, and then I'll do the same thing I did before. I'll say pred boost equals pred boost greater than 0.5. And what this does, just like the line 20 here, I'm just converting my numerical probabilities of the target being true to actual trues and falses. And I have to use the same cutoff probability in both cases in order to compare both of them, like objectively compare the two of them together. So I can do the same thing as I did earlier. I'm just going to copy paste here and give it a different suffix. So rather than RF, I'm going to use boost. Everything else looks good. And I'll move my face back down. Notice in this case, they have exactly the same error rate. And I always worry about that. And the way I would check if I were doing this for real to make sure that I didn't have some subtle error is run the whole thing again. And if they have exactly the same error again, I should be worried. But notice they don't. They're just close. See this thing? They're actually different now. If we run it again, they're different. So it just could be that these are pretty similar. Like they're just pretty similar model strengths. And so therefore, sometimes their model, and it's a small data set too, so those exactly equal things happen more often when the data set is a little bit smaller. But it's not always the case for different training and test partitions, which is good. So what else? I think that's it for this one. It should be looking good. You can also see that as we run this different times, there's already trading back and forth about which one's better. In this one, the random forest was better, but in other ones, they're the same, and other ones, boost was better. So it seems like it depends on the exact training and test partition. Yep, there's one where the boost is better. But notice that both of them are significantly better than the benchmark. So in the final video for this section, we need to implement stacking, which is a little bit more complicated, not because the method is more complicated, but because there's some kind of tricky steps that we need to be careful of. So I'll save that one for another video and wrap this one up for now.